Module 6, radical functions and their equations, and the first topic that we're going to talk about is the graphs of radical functions and their transformations. More specifically, we're going to get into two parent functions, graphs of radical functions, and then what happens when they move around, and then the domain and range of all of the radical functions that we look at. So I broke this up into two objectives. The first objective is to graph the parent radical functions and then become familiar with them. The second objective is to find the domain and range of radical functions and then look at and see how they move or find their transformations as well. I broke this up into two videos. The first video is just going to be objective 1. So to begin this video, let's look at some basic perfect squares. And we're not going to look at perfect cubes, just perfect squares for now. So, because the perfect squares are important for this, because we're going to be looking at the square root of an input. The first parent function is y equals the square root of x. So I want to find numbers that if you take the square root of them, it'll give you a whole number for an output. So let's talk just briefly. 1 squared means 1 times 1, and it's 1. And the square root of 1 is 1 as well. So the first perfect square is 1. 2 squared is 4. The square root of 4 is 2. So the next perfect square is 4. 3 squared is 9. 4 squared is 16. Again, because the square root of these numbers gives me a whole number for an answer. So again, the first 4 that I care about are 1, 4, 9, and 16 of perfect squares. All right? So let's look how those interact with the graph itself. The first parent function that I care about, and again, this objective is to graph the parent functions, is y equals the square root of x. I'm going to use my perfect squares as the inputs, and again, inputs are the x values. So I'm going to write 1, 4, 9, and 16. All right? If I input these x values into my function, I will get y equals the square root of 1, y equals the square root of 4, y equals square root of 9, and y equals the square root of 16. So, in that then, the math that I do for each one of those, the square root of 1 is 1. Square root of 4 is 2, the square root of 9 is 3, and the square root of 16 is 4. So if you look, the first 4 perfect squares give me an output of 1, 2, 3, and 4. So those are the only 4 that I want to work with, because now I can go ahead and graph this radical function. All right, it always starts at the origin, 0, 0. And it's important to notice, and I'm going to write this up here, the vertex of this and the vertex of every parent function we're going to work with in this module is going to be 0, 0, x and y. That's where it begins. So 0, 0, the first plotted point is over 1, up 1, over 4, up 2, and over 9, up 3. So this is my radical function. Just like that. Goes on forever in the right direction. Now, radical function, it's sometimes talked about. A good way to remember this is the graph looks like a sideways parabola, half of a parabola. Because if you remember, I'm going to write y equals the square root of x, what I just graphed in blue, and then in green, y equals x squared. Square root of x and x squared are inverses of each other, and if you remember the graph of a parabola, something like that. If you can visualize, the square root is half of that, and it's kind of on its side, just to consider. And we'll talk more about inverses later on in this module. So what I drew in blue right here is y equals the square root of x. We need to become very familiar with that because we're going to base all of the next objective, the transformation in the domain and range, off of this function y equals the square root of x. Now, the other function we care about, and care about because it is a radical, but I'm going to work more with the square root, I just want to show you this one as well, is the cubed root of x. The cubed root of x plays out a little bit differently, mainly because cubing numbers and taking the cube root looks a little bit different than squaring numbers and taking the square root. But I've given you the inputs here, -8, -1, 0, 1, and 8. -8, the cube root of -8. I want you to try this, all right, just to see what the relationship is. If you plug in the cube root of -8 into your calculator, it will give you an output. So I'm going to show you how I would do that, and then I want you to find the rest of these outputs down here. All right? So if I was going to plug that in the calculator and find the output for -8, and taking the cube root, I'd pull up my calculator, and then on the left-hand side, if you see this math button, you go down to number 4, or you can hit 4. That brings up the cube root option. And I want the cube root of -8. And that gives me -2. So that process I just did on the calculator, you're going to do for the next 4 just to see what the outputs are. So -2 is my first output that I care about. So I'm going to write this in green. So at this time, please pause the video and tell me the next 4 outputs, just so you can get this process down of entering that into your calculator. So at this point, you should have paused the video, and please now check your work with mine. These are the next 4 you should have gotten. -1, 0, 1, and 2. Hopefully you entered that in the calculator right, and that's what you got for the next 4 outputs. And if you notice, there is a pattern. The vertex is here, like I mentioned earlier. A graph always starts at 0, 0. A parent function always starts at 0, 0 right there. And if you see, they already drew the graph for us. But let's see if these lines match up. If I take the square root of cube root of -8, I'm going to get -2 as an output, and it matches. Cube root of -1, I get -1. Cube root of 0, I get 0. Cube root of 1, I get 1. And 8, I get 2. So it is drawn correctly. And if you notice, it looks like a S shape. And whatever it does in the negative X area to the left of the y-axis, it's going to do the same thing to the right of the y-axis. And this y equals the cube root of x is considered to be odd because it flips about the origin here. Meaning if I were to draw this piece over here and then flip it again down here, it would be the same exact thing. So it is odd. So these are just an introduction to the cube root and the square root parent functions, and we're going to be working with these in the next objective. Mainly we're going to be finding the domain and range and looking at transformations based off of the vertex that we find for each function. Now before you end this video, go ahead and pause and tell me the domain and range of this function. This should be reviewed from Module 4 of polynomials. So at this point you should have paused and tried the domain and range on your own. Again, the domain is the left to right motion, the x value is an x-axis, and if you see this graph goes on forever in the negative direction, and it goes on forever in the positive direction. So, it is negative infinity to positive infinity are all real numbers. Range, same thing in this case. It goes to the left forever, but it also goes down forever. So it goes from negative infinity, goes to the right forever, but also goes up forever to positive infinity. And we're done. So I can also label this all real numbers as well. So please consider that the cube root of a function, any function, parent function or not, the domain and range will always be the same. It's always going to be all real numbers for both because it's continuous and it goes on forever in every direction. Now, the parent function of y equals the square root of a function or of inputs or an x value, it's a little bit different. If you notice, it goes on forever in the right-hand side, but it stops going to the left and stops going down. So it's going to change the left value of the domain and the left value of the range. And we're going to talk about that in the next objective.